In this video, we're going to talk about hybridization and the hydrocarbons. Okay, the learning competency here is to describe the bonding in ethane, ethene, also called as ethylene, and ethyne or acetylene, and explain their geometry in terms of hybridization and sigma and pi carbon-carbon bonds. It sounds so complicated, but we're going to get through this. Let's go. Let's talk about the atomic orbitals of carbon. Okay. A carbon atom does not form ions easily since it has four valence electrons. Again, valence electrons are the electrons in the outermost shell or the electrons in the highest energy level. If this is the electron configuration, these are the valence electrons. Okay, so four valence electrons. One, two, three, four. These pictures show the orbital diagram of carbon. As you can see, you only have two free electrons for bonding, 1 and 2, right? So how can carbon have four bonds and follow the octet rule?
I know a lot of things, but I don't know about that.
Basically, it satisfies the octet rule in compounds by sharing electrons. These are the orbitals that exist on atomic carbon. Take note that they are not connected. So what happens when it bonds? When carbon atoms form bonds with each other, we describe the resulting bonds using hybrid orbitals. Hybrid orbitals are formed by hybridizing the carbon's atomic orbitals in a process called hybridization. Hybridization is just a fancy term for mixing. Okay? So when carbon atoms bond two other atoms, the 2s orbital and all three 2p orbitals in the valence shell combine to produce four sp3 hybrid orbitals. So how did it become like this? So let's look at the orbital diagram of carbon. This shows carbon atom in its ground state. Again, the ground state configuration is the lowest energy. It is the most stable arrangement. When it undergoes excitation, this electron in the 2s orbital will be promoted to 2p, giving us the excited state of carbon. Then the 2s and the 2p will hybridize to form sp3 hybrid orbitals. So this 4. Okay? Again, they are called carbon sp3 hybrid orbitals. So why sp3 hybrid? Hybrid means mix, and this s orbital mixed with these three p orbitals. That's why we have sp3. On a shallower level, it's like this. So this is a carbon atom with its four valence electrons, or the sp3 orbitals. They will bond to four hydrogen atoms to have an octet. And we know that hydrogen has s orbital. So when they bond, they will now have sp3s overlap. Okay, this one. sp3s overlap. This, actually, we have a name for that. We will discuss it later. In the orbital diagram, it looks like this. So this pink one is from the hydrogen. Now, in order to get as far away from each other as possible, the sp3 orbitals are arranged in the shape of a tetrahedron or tetrahedral. So the angle here is 109.5. So it looks like this. So again, this molecular shape minimizes the electron-electron repulsion. We have studied this in VSEPR theory. In organic chemistry, this molecule is called methane. Methane has a chemical formula of CH4. Methane is the simplest hydrocarbon consisting of one carbon atom and four hydrogen atoms. This is a powerful greenhouse gas which is flammable and is used as fuel worldwide. Now, what are hydrocarbons? You have learned this in your lower science subjects, such as earth science. Fossil fuels are hydrocarbons. So hydrocarbons are substances containing only carbon and hydrogen. Hydrocarbons are classified into the following major categories: alkanes, alkenes, and alkynes. But we have the fourth category called aromatic hydrocarbons. In the following slides, we will do an overview of the basic characteristics of the first three. Okay? but we will postpone the study of aromatics for the next videos. Alkanes are hydrocarbons where all bonds are single bonds and all carbons are tetrahedral. So methane is the simplest alkane. Okay, so the carbon chain constitutes the basic skeleton of alkanes. Carbon chains with four or more atoms can be linear or branched. Okay, so again, four carbon or more. Some examples are shown below. This is for the linear alkanes, and this is for the branched alkanes. Okay, so this one is the methane. Now, if you have two carbons, you will have ethane. One, two. That's why it's C2. Okay, three carbons will give you propane. Okay, so they are all linear. And this one is butane. Butane here has four carbon atoms, but it can be branched, as you can see here. C4, but it has branch. So if this is the formula, if this is the structure, it is isobutane. Okay, if you have one branch here, it is isopentane, C5. As can be seen from the examples, all alkanes have the general formula CnH2n plus 2, where n is the total number of carbon atoms. Meaning, if you have 5 carbon atoms, you will have 12 hydrogen. So this is the formula for alkanes. When atomic orbitals of different atoms overlap to form covalent bonds, they may approach each other in two major ways. We have the head-to-head overlapping and the sideways overlapping. Only head-to-head overlap is possible with s orbitals because they are spherical. Okay? Hybrid orbitals also undergo mostly head-to-head overlap when forming covalent bonds. P orbitals, on the other hand, can approach each other sideways or head-to-head. For this part, our only concern is the head-to-head overlap, because that's the only type that occurs in alkanes. When orbitals approach each other in the head-to-head fashion, the resulting covalent bonds are now called sigma bonds. So it looks like this. Okay, so this methane here, CH4, has sigma bond here. Okay, this is sigma bond, sigma bond. And if you remember, this is what we called earlier the sp3s overlap. Okay, now let's consider ethane. So again, ethane has the formula C2H6. We can draw ethane like this. We have the sigma bond between the sp3 hybrid orbital and the s orbital, right? So we have this. Now these two sp3 carbons overlap to form a carbon-carbon sigma bond. So these two sp3 orbitals overlap head-to-head, forming this molecule. Here, you now have a sigma bond between two sp3 orbitals. Okay, so question, how many bonds are there in C2H6 or ethane? There are 7. 1, 2, 3, 4, 5, 6, 7. Okay. In alkanes of 3 carbon atoms or more, the main carbon chain acquires a zigzag structure due to the 109.5 angle between the carbon-carbon bond, such as in propane. Again, propane has 3 carbon atoms and 8 hydrogen atoms. Okay, so these figures show two representations of propane, where the zigzag structure of the carbon chain becomes apparent. So it looks like this. Ta, ta. Now, if you're going to extend it more or add more carbon atoms, it will go like this. So for long chains, writing the Lewis structure or even the condensed formula will be tiresome. So a shorthand notation that uses zigzag lines has been developed. This is called the line angle formula. Okay? The arrows point to the position of the carbon atoms, and this is the equivalent in condensed formula. As you can see in the line angle formula, the symbols for carbon and hydrogen are not included. Now, consider the bonding in boron trifluoride. Since boron is the central atom, we'll focus on boron. Remember, the electron configuration for boron is 1s2, 2s2, and 2p1 because boron has an atomic number of 5. So when you add this, it's 5. So if we're going to draw the orbital diagram of boron in the second energy level, we will have this. Question now is how can boron form 3 bonds with fluorine when it has only one unpaired electron?
I'm so tired. I'm so tired. I'm so tired.
Because the energy gap between the 2s and 2p orbitals is small, one of the electrons in the 2s orbital can be promoted to the 2p orbital via the unpairing and excitation process. So we will have this. Now the 2s and two 2p orbitals can be mixed to form 3 sp2 hybrid orbitals. Like this. sp2 hybrid orbitals. Okay. And if we're going to look at the molecular shape, it is like this. So one s orbital, 3p orbitals, they will form 3 sp2 orbitals, plus the one unchanged p orbital. Okay, the sp2 hybrid orbitals have a trigonal planar orientation. Therefore, all are on a plane with the angles of 120. Take note that in sp2 hybrid orbitals, you have one unpaired p orbital. So if you're going to draw the molecular geometry of BF3 or boron trifluoride, you will have this. This is 120. This is 120. Now let's consider the bonding in ethylene or C2H4, also called as ethene. This is the lowest structure for ethene, and from this, we deduce that the geometry around each carbon atom in ethene is trigonal planar. So this has 120 degrees. The valence electron configuration of carbon using orbital diagram is shown by this figure. So remember, for trigonal planar, the hybridization used is sp2, as we have discussed earlier. So let's see how it happens. Let's look at the second energy level. So one electron from the 2s orbital is promoted to 2p. So we will have this. Now, to form 3 sp2 hybrid orbitals, one 2s orbital and two 2p orbitals will mix. So we will have this, sp2 hybrid orbitals, and we have 3 of them. But if you notice, one unpaired electron will be left in the 2p orbital. Now, this is the top view of this arrangement, the trigonal planar. So for us to see the unpaired electron, let's switch it to a side view. So we will now have this one, the sp2 hybrid orbitals. And this is your unhybridized p orbital. Now, when two sp2 hybridized carbon atoms approach each other to form a bond, two sp2 orbitals approach each other head to head. Okay?
So I am confusion. Why is this one?
And two p orbitals approach each other sideways. So now it will look like this. The bond formed by sp2 orbitals is a sigma bond, and the bond formed by the p orbitals is called a pi bond. So this illustration tries to convey a basic feature of the pi bond as compared to the sigma bond. So the sigma bond is short and strong. As a rule, head-to-head overlap is the most efficient way to bond and results in a relatively strong and stable bonds. The pi bond, on the other hand, is relatively long and diffuse. So remember, sideways overlap is less efficient than head-to-head overlap and results in formation of weaker bonds. This has some implications in the properties and chemical reactivity of sigma and pi bonds. This is another picture of the sigma and pi bonds in ethene or ethylene. The electrons in the sigma bond, or sigma electrons, are more tightly bound to the nucleus and don't move too much. In other words, they are more localized. The electrons in the pi bond, or pi electrons, are less tightly bound by the nucleus. Therefore, they are relatively mobile. Under certain conditions, they have the capability to become delocalized, meaning they can move in the molecular skeleton from one atom to another, or even become spread over several atoms. At the same time, in chemical reactions where electrons are to be traded, the pi electrons are more readily available because they are more exposed and less tightly bound by the nucleus. So they are alkenes. Alkenes are hydrocarbons that contain at least one pi bond as part of their molecular structure. Again, one pi bond. By this definition, the simplest possible alkene must contain two carbon atoms, and it is called ethene or ethylene, which we have discussed a while ago. So here is a Lewis and a line angle representation of ethene. Notice that although CH bonds are not usually shown in line angle formulas, sometimes they are included for enhanced clarity. Alkenes have double bond. Okay, double bond. Just be cautious about the Lewis representation. They do not differentiate the sigma bond and the pi bond. So let's have more examples. We have propane, 1-butene, 2-butene, cyclopentene, cyclohexene, and benzene. So if you notice, alkenes end in the suffix "ines." So we will study more of this when we go to nomenclature. Okay, so these molecules or these compounds are called cyclic structures. Okay, and if you notice, the general formula for alkenes that do not form cyclic structures and which contain only one pi is C2H2N, where N is the number of carbon atoms. For example, your N is 3, so your hydrogen is 6. So this is propene. So 1, 2, 3 carbon atoms, and 3, 4, 6. Now let's talk about alkynes and sp hybridization. The process for understanding the sp hybridization for carbon is basically an extension of the other two types, sp3 and sp2. So try to use that concept and practice to see if you really got it. Now, remember, sp hybridization gives rise to the formation of hydrocarbons known as alkynes. Alkynes contain at least one triple bond and have linear geometry around the carbons comprising the triple bond. Therefore, the ideal angle between the sp hybrid orbitals is 180 degrees. Some examples include ethyne, propyne, butyne, and 2-butyne. Okay, so here just remember in alkynes you have two unpaired p orbitals. That's why you form the triple bonds. If you notice, the general formula for basic alkynes is CnH2n minus 2, where n is the total number of carbon atoms. So let's consider again propyne. So if you have 3, your hydrogen is 4, because 3 times 2 is 6 minus 2, 4. If we're going to check this, you have 1, 2, 3, correct? And 3, 4, correct. To summarize our discussion, we have this. In sp3 hybridization, you have 4 orbitals, and the shape is tetrahedral geometry. Okay, they are single bonds. In sp2 hybridization, you have 3 orbitals, trigonal planar geometry, and the angle is 120. You form double bonds because you have one pi. In sp hybridization, you have 2 orbitals and you will produce a linear geometry. So the angle would be 180 and you have the triple bonds because again you have 2 unpaired p electrons. So this is the 6 types of carbon-carbon sigma bonds. So sp3, sp3 between sp3 carbon atoms. You also have sp3 and sp. This one is CH3. And this one is sp because you have triple bond. You have sp and sp2. This is triple bond. This is sp2 double bond. Okay?
Rigor Morris, girl. It was rigor Morris.